Thanks a lot, everybody, for partaking in our seminar today. It's my great pleasure to welcome Dr. Kelin Wang from the Pacific Geoscience Center of the Geological Survey of Canada and the School of Earth and Ocean Sciences at the University of Victoria. Kelin got his bachelor's degree at the University of Beijing and then did a PhD at the University of Western Ontario. He is one of the world's foremost experts on subduction zone megathrust dynamics and the behavior of the solid and sometimes not so solid Earth. His work has been recognized by a number of awards. He is a recipient of the Tuzo-Wilson Medal of the Canadian Geophysics Union. He was the Birch Lecturer at AGU, and he's a fellow of AGU, among other honors. Dr. Wang is really exceptional in his capabilities of integrating a range of constraints, geophysical and geological, into simple but very elegant and insightful models on how subduction zones work. And he does so in a way that is really quite unique in terms of speaking both to seismic hazard and to understanding of rheology on regional all the way up to global scales. So it's a great pleasure to have Kelin here in town. I'm looking forward to his presentation and the further discussions. He's going to talk to us about earthquake deformation in a viscoelastic earth. Kelin.
Thank you, Thorsten, for the invitation and for the kind words. And is the sound okay? Okay. Yeah, it's nice to be here. It's actually my first in-person seminar since the pandemic. Yeah, I went to a meeting but didn't give a seminar. I just had conversations. Yeah, my first one. It's a pleasure to have it here, and I hope to talk to some of you and get your feedbacks and learn from you about the exciting science you are doing. So what I will talk about is the earthquake deformation in the viscoelastic earth, and many people have contributed to this work over the years. Mostly a number of former and current PhD students. We know the Earth is not advancing slides. I guess okay, it's been slow. We know the Earth is viscoelastic first from its response to glaciers, right? When the ice melts, the Earth does not rebound. There's a delay, and that delay indicates the Earth has a viscous behavior, this mantle flow. And from the global analysis, now is commonly recognized if the mantle viscosity is described as Newtonian, and the value is of this order, so it's many, many orders of magnitude higher than honey at room temperature. Of course, it's still solid rock, right? And for earthquake cycles, and we have the same behavior. And in that case, this just for subduction zone, in that case, the viscosity of the mantle wedge, after many years of study, is recognized to be lower than the global upper mantle average by about 1 or 2 orders of magnitude. And of course, there's also, because for the short time scale, there's also the issue of a transient rheology, and I will not emphasize that aspect in this talk. Okay, for today's talk, I'll make 4 points as summarized in my abstract. Let's start with the first one and the bigger picture, and I'll describe how and why the upper plate of a subduction zone will reverse direction progressively as time goes, as controlled by mantle rheology and megathrust locking. After a big megathrust earthquake, and there are 3 things going on, right? And what's most important for this seminar is the viscoelastic stress relaxation. And that's dominant right after the earthquake. And also important as time goes, and the effect of the relocking of the megathrust will become increasingly important, will become dominant as time goes. And the computation of these two will cause the reversal of the upper plate motion, right? At first, we have the motion, opposing motion this way. Eventually, the locking effect will become more dominant and relaxation effect will become weaker. And we'll see stations here on land, reverse direction that way. And there's also the effect of after slip, the continued motion of the megathrust and in different places. And that can be important also after the earthquake and in different places. That's more of a site-specific process. I will not talk about this in this talk. So focus on the other two processes. So talking about the stress relaxation after the earthquake, the best observations probably are from Japan. And that's the 2011 Tohoku-Oki earthquake, which caused a devastating tsunami. At the time of the earthquake, and they had numerous GPS stations, they recorded motion, seaward motion that way. But after the earthquake, this is postseismic motion. You see the stations on land continue to move seaward, but these stations offshore, they change direction. They are moving back. That's the opposing motion I was talking about. But in this case, the subduction goes from right to left, and so it's actually this way. So we have this opposing motion here. Okay, and we can, of course, we can model this. Actually, after this this many years, thinking back, it's not a hard job. We can model this with pretty simple model with all these parameters. I will not explain. There's different viscosity values and the structure, subductional structure. It's a 3D model, and of course, with these models, we can reproduce observations. So this is the comparison of model and with the observations a year after the earthquake. You see these stations moving backward. And the model would predict that a couple of years later, and while also confirm the observations, and we'll have this kind of motion. And what's important is the dividing boundary of the opposing motion. Even in a couple of years, you notice the boundary has already moved a little bit. Here is here, but a couple of years later, it's actually moved landward a little bit. And that motion will continue. In about 20 years after the earthquake, it'll arrive on the coast. So about a decade from now, we'll begin to see the coastal stations turning around. Yeah, to go the other way. And that motion will just continue. That dividing boundary will continue to move that way until everything goes landward. So that's the progressive reversal of direction I was talking about. And the reason is, of course, mostly viscoelastic relaxation after earthquake and the increasingly dominant effect of megathrust locking. That's the right here, right? And as the effect of megathrust locking becomes larger, we'll see stations moving the other way. But Japan, for Japan, we only had about 10 years of observations, but we can see the same effect from other subduction zones. We take a snap, each subduction zone, what we observe today is a snapshot of the given time of the earthquake cycle of that subduction zone. So we see different places have this behavior, consistent behavior. Like a couple of years after Sumatra earthquake, see all these stations were still moving seaward. Of course, we did not have stations further offshore to show the opposing motion there. And a few decades after big earthquake, that's the Chile earthquake, and we see the opposing motion. And here the dividing boundary is actually here, right, as confirmed by the observations. And as time goes, and this is Cascadia, 300 years, everything moves the other way, right? And it already passed all these stages. But these are for the big earthquakes. And to verify that the physics really works, it should also work for smaller events. So what about smaller earthquakes? Okay, now we can take a look at these other events where we have enough observations. So what I've described is something like this. Suppose we have 3 stations here. So the early stage after the earthquake, and we have opposing motion between these 2 stations here. As time goes, that boundary of the opposing motion will move landward and will become between B and C. As time goes further, and everything will move the other way. So we want to see and the boundary of this dividing boundary, when the boundary will pass through a reference location. So we pick this location, which is the surface projection of the 50-kilometer contour of the interface. We pick this location as a common reference for all these earthquakes. What we want to see and what time that dividing boundary arrives at this location. We call that time the reference time. So we've modeled all these earthquakes. Now we just take a couple of examples. Let's first start with the Maui earthquake, and not too big, not too small. And for this earthquake, and the dividing boundary of the opposing motion passed through the reference location in about a decade. And as you can also see from the limited continuous GPS stations here. But if the earthquakes are smaller, the motion, the dividing boundary arrives at that location much faster. So for magnitude 8 earthquakes, it takes only about a year or 2 to get there. It turned out with all these earthquakes, we see this trend, and the reference time, the time that the boundary arrives at the reference location will increase with the magnitude of the earthquake. And the reason is, and the smaller earthquakes will cause smaller stress perturbation, which will take less time to relax. And the locking effect becomes dominant more quickly. So that's why we have this trend. Okay, so that's the reason. And as you can see, and in this picture, the largest earthquake is, of course, the 1960 Chile earthquake. And it takes 4 decades and for the boundary to arrive at the reference location. And that is the Chile picture here. That's what we see today. And this is the opposing, the boundary of the opposing motion right here. It has gone through these stages as we can back predict with the models. And that boundary will continue to move. And after many decades, or maybe 100 years, and it'll move to a much further landward, and all the stations will eventually turn the other way around, just like what we are observing at Cascadia today. And however, there came a surprise. And some of the stations in the south reverse direction quickly. So that brought up my second point, the premature reversal of southern Chile, indicating enhanced locking. Okay, for southern Chile, here came our 3 APC stations again. And what we are observing today is here, right? Southern Chile at this point. And the opposing motion should be here, right? But this Becker station here, station C, and is supposed to be moving that way for many, many decades. However, surprise came, and see these stations indeed were moving that way, right? Seaward. And this is the only continuous station, and just around the turn of the century, here we see this station decelerated and eventually actually a little bit reverse direction. And that reversal was way too early and way too rapid. And in no way could be predicted by any viscoelastic model. And so at the time, we thought it might be something wrong with the station itself. Maybe the station was unstable or whatever. So it took us a few years of wondering. And then some of our colleagues installed some new stations to try to see what happened around it. It turned out, and it is confirmed by many other stations. And this picture is very difficult to see, right? There's older measurements and new measurements. And it's easier to see it this way. If you compare older and newer measurements, you'll see there was a eastward increase in velocity fairly quickly, right, between the two measurements. And so that motion, the eastward or the reversal, that eastward increase in motion was confirmed what happened regionally, not just by that one station. That one station is here, that's the dashed line here. And there's so far, no mental rheology can explain the rapid change. So out of desperation, we proposed that it might be produced by a sudden enhanced locking of the megathrust. Suppose, and the deeper part of megathrust that was creeping for some time, for some reason, for fault mechanics, we don't really understand, it became locked. And that locking can produce and the surface motion like that. And the motion before and plus this motion will give rise to the motion now. So this station, see, has changed direction. And that little enhanced locking can readily produce this picture, like enhanced eastward motion this way. Okay, so that's the story about the enhanced locking reflected by the early reversal of these stations. That's all about horizontal. Now for the next point, I'll talk about the vertical. And now let's take a look at the vertical motion at a shorter time after the earthquake, short-term postseismic. And still the same subduction zone, but slight different location for the same earthquake, slight different location. And that's vertical postseismic motion as geodetic signature of cold forearc mantle wedge. Now we can see how geodetic observations can provide information on the thermo-petrological properties of the subduction zone. Okay, so that was the rupture slip distribution of that earthquake, the most recent model. And these yellow vectors were monumental observations made by George Klafker, USGS. He went there and went up and down the coast and did field surveys, interviewed residents, local people, and to figure out the vertical motion of the land after the earthquake. And that set of data really helped establish the megathrust earthquake cycle story, and it was a milestone in the development of theory of plate tectonics. But however, and at that time, there was a set of observations here, just near the volcanic arc. And they were they all went up here. And for a long time, these observations were thought to be co-seismic or produced by the earthquake all of a sudden. But no co-seismic deformation model can ever explain it. You see, in this model, actually produce some co-seismic subsidence instead of update. And so that has been a mystery for the past half a century. Now we can understand it. To explain why this happens, let's first start with the thermo-petrologic field of the subduction zone. What's the most fundamental for subduction zone geodynamics is the thermal contrast between the very cold forearc and very hot arc and back arc. And it's because of the change in the way the slab and the mantle wedge is coupled. And from a certain point, they are fully coupled, induces this mantle flow that brings in hot material from the back arc at greater depth to make the temperature very, very high. We see high heat flow here, and here the forearc, because the subduction is very cold, it's cold enough to for hydrous minerals to be stable, and here it's hot enough to produce to allow arc volcanism. So the contrast is very sharp. So in association with this petrologic contrast, there is the mechanical contrast. And that cold forearc mantle wedge can be described as an elastic nose. We call it elastic cold nose for the time scale of earthquake cycles. For like 300 years, 1,000 years, yeah, it's just elastic. And this much hotter one and is viscoelastic. And the observation we are talking about is here, right around the edge of the cold nose edge, CNE here. Let's see how it works. Suppose we can use a simple model here with this kind of cold side slip distribution. And 5 years after the earthquake, the surface deformation, vertical deformation will be like that. And this is without the cold nose. So without the cold nose, you see barely any vertical uplift here, right? But if you have the cold nose, things will change. The cold nose will cause the mantle flow due to a viscoelastic relaxation to be more difficult to go seaward. So it's deflected upward to cause this uplift. See, no cold nose with cold nose. So that's the difference. That's why. And we look around the world to see if that pattern is seen in other earthquakes. And so far, we have not seen any exceptions, right? But only a few earthquakes provided enough data for us to do some modeling. And these are the model results that includes the big earthquake I was talking about, and the Maui earthquake I was talking about too, and also the most importantly, the Chile earthquake. And these are not GPS measurements. These are George Plafker's geological observations. Uplift. Now we understand what happened, and it was considered to be co-seismic, but notice, and his observations were made 8 years after the earthquake. There's actually, that includes 8 years of post-seismic deformation. Now we understand these uplift actually indicate post-seismic viscoelastic deformation in the presence of the elastic cold nose. So the 60 years of scientific mystery has been resolved. Now with the cold nose, we can, with 8 years of post-seismic uplift, we can explain the data rather readily. So that's the third point. Now we've gone through the horizontal motion and the vertical motion for different reasons. If you look further in the future, you will notice the deformation actually slows down. So the strain rate will decrease. The strain rate decreases time. What's the implication to earthquakes, for the potential of a next rupture? So that's a fundamental question. And to explain this question, I'll change to that's the fourth point, decrease in deformation rate over interseismic period, and the relevance and geodetic observation to earthquake potential. To address this problem, I'll switch to a simpler model because the physics is the same. Now I'll look at a strike slip system because the same physics is once explained can apply to subduction zones, but it's much simpler to handle. And this is observations for many strike slip fault, interseismic observations. And what it shows is interseismic stream accumulation like that. And the time for earthquake, the stream will recover like this. And that can be, it's often modeled using an elastic model like this, and with prescribed motion below, and the fault is locked. You have this kind of deformation. That's only half of the picture here, but about this half. It's a very simple solution, and with certain locking depth. So that can explain a lot of the observations for strike slip faults. but there are very noticeable exceptions, such as the Eastern Altentak fault and here, and there's no way the observations can be explained by the elastic locking model like that. And to explain these kind of observations and to understand the broader picture, and we have to introduce viscoelasticity as what we did for subduction zones, right? And this is the simplest viscoelastic earthquake cycle you can ever imagine. It's just a simple vertical fault here, and with the elastic plate, with the viscoelastic substrate, with this viscosity and rigidity, and the relaxation time is like that. And with a periodic earthquake cycle, nothing can be simpler than this for a viscoelastic model. If the recurrence interval is short as compared with the relaxation time, right? For common viscosity of upper mantle, relaxation time can be 10 years or 50 years, something like that. If the earthquake cycle is short enough in comparison, and you can see, and after half the earthquake cycle here in the middle, we have this deformation or velocity distribution dashed line, and just before the next earthquake, as time goes longer, at this point we have this one, and they are very similar. They're similar to what is described by the elastic model, right? But if the recurrence interval is longer, the picture will be different. See, if now the recurrence interval is much longer, 20 times the maximum time, now you can see, and half of the earthquake cycle, the distribution, the deformation is much more distributed than described by the elastic model. And just before the earthquake, there's not much deformation going on. I shouldn't say not much deformation rate going on. So what happens to a strain accumulation to produce earthquakes? And this cannot be compared with a common picture like that. Actually, what the observations, suppose the GPS can only observe this, but this is the rate. So what we can observe with geodetic measurements is only how fast or how slow the strain energy is accumulating. It's not the strain energy itself. The strain energy itself is the deformation itself, right? Displacement, right? So that's the velocity or the rate of displacement, and this is displacement itself. And it's the displacement that tells you the energy, right? From the last row, how much energy is being, and the slope, of course, near the fall, the slope of the displacement is the strain rate, and that tells us the strain, then the strain energy, elastic strain energy, and half of the earthquake cycle, the slope is like that, and for this blue line, long earthquake cycle event, half of the time, the slope is much higher, the strain energy is a lot more, right? So it turned out that if the recurrence interval is long, most of the strain energy required to propel for the next earthquake is accrued in the early part of the interseismic period. And the deformation rate reaches a minimum before the next earthquake. So what we observe with GPS, with geodetic observations, is the rate. It'll slow down, but the strain rate the strain energy has been accumulated a while ago. So that's the story. Now we can go back to our Altentak fault. As we see, the elastic model cannot explain it. With the viscoelastic model, now we can produce it, either half of the cycle or assuming we're already at the end of the cycle, we don't really know, no matter what. And the viscoelastic model and with this concept can explain observations much better than the elastic model. Of course, it cannot explain every point because of simplicity of the model and errors in the data, but the concept is there. And see, at the same, even the rate of deformation is low, or the strain rate is low, the actual strain, as reflected here, is is quite high. So there is enough energy for the next earthquake. So that applies to all earthquake cycles, including subduction zones. So back to Chile, and even though we haven't modeled it, but we can understand conceptually that, and as the time goes, the strain rate will continue to decrease, but actually the strain energy in the system continues to increase, but the rate of increase becomes smaller and smaller. So the system will be ready, maybe, yeah, for next earthquake and sometime. And the implication, there's some implications for this concept. And for example, and for seismic hazard analysis, normally is time independent, was assumed postponing earthquake recurrence, right? Doesn't matter. So the occurrence of next earthquake has nothing to do with the previous earthquake. That's the basic time independent hazard analysis. But the time dependent analysis considers accounts for the earthquake cycle. So how much energy has been accumulated since the previous event. And so there are time-dependent analysis methods, and commonly you have to assume a certain basic, like sawtooth function. Then you have introduce some Brownian perturbation and produce these things for analysis. And so, and that it turned out that the sawtooth function works quite well for if the recurrence interval is short. And the last model is fine, right? But recurrence interval is long and it's no longer sawtooth. It is something like this. And most of the energy is accrued early in the cycle. And so these are the things that need to be done, but not done yet. Okay, so I've made my 4 points, and the progressive reverse of motion direction in upper plate for subduction zones, and controlled by megathrust rheology, megathrust locking. And the premature reversal in southern Chile indicates enhanced locking, but the mechanism not understood yet. And the vertical deformation of postseismic motion can be a geodetic signature of the cold forearc mantle wedge. And that I think is quite well understood. And the decrease in deformation rate over intra-seismic period, and the relevance of geodetic observation to earthquake potential, and still need to be better studied. That's my talk. Thank you.
Thanks a lot, Kelin. We got plenty of time for questions.
Hi, thanks for the really interesting talk. I have a question about the vertical motion in the cold nose area. So it looked like on your map, some of the vertical stations were pretty much on top of volcanoes. So I was wondering how you explain like something that's cold enough to have this vertical uplift, but hot or wet enough to have arc volcanism.
Yeah, these stations are on the coast, right? Because of the zigzag shape of coastline there, the complex geography there. George Parker was able to observe either the little things that indicates uplift or subsidence, or talk to people in that area to see what they noticed. Yeah. And so these are the question is they're not on volcanoes themselves, they are on the coast. And but of course because the crust is certain thickness, right? And any deformation is always there's certain wavelength, right? And when the uplift is always produce uplift here and there as well.
Right, but where is that wedge with respect to the volcanic arc? I guess that's Edward's question. In your cross section, you had like a sketch, yeah. So
yeah.
So is
Yeah.
where where's
It kind of did. So that's the claim, right? And I think that we've made a claim and years ago, but I think it's pretty well accepted by the community that the remember there's a decoupling and coupling transition. We made a claim that the transition occurs about 70 to 80 kilometers depth for all subduction zones, with exceptions. Yeah, if the subduction zone is not mature or whatever, right? Normally it's around that depth.
right,
And so
that's trenchward, right, of the arc, because the arc is at 100, right?
that's right. That's right. Yeah. And so and the distance depends on the dip of the slab, right? If it's mostly dipping, it's closer. And yeah.
Okay, thank you.
So if we can go back to the analysis where you showed that the reversal time scales with earthquake size, and you suggested that that's because the large events have a larger stress drop. Now, I wonder if you sort of dug into that with a simple mechanical model, because we know that stress drop isn't that variable. And so there may be something, whatever, between 1 and 10 or 30 MPa. And so another option would be, and you could of course infer that from the co-seismic subdistribution, is that the larger events are sensing deeper, for example, and you might be sampling different viscosity structures.
Yeah.
So how convinced are you that this is actually the stress causing that difference?
Well, actually, when I say a larger stress perturbation, I was actually including that aspect. And not only the magnitude is larger, also the area, affected area is much bigger. So thank you for clarifying this. And the other thing I want to make it simple. And one is the stress. Yeah, you have a larger stress perturbation that goes a lot deeper, so it takes time to relax, right? And the other important aspect is the 3D versus 2D issue, right? You assume it's very, very long rupture, right? And the mantle flow due to caused by relaxation is essentially 2D, right? If it's a smaller rupture, then the flow can come in to fill the hole, right, more quickly. So there are two things. One is stress, the other is the flow pattern.
I guess I wonder, can you draw some sort of line on that plot on the right? Right. So realizing that these viscoelastic relaxation problems are regrettably a little bit annoying in that if you have layering, all of a sudden it becomes a little bit tricky to determine where the Maxwell time actually applies. And so, but you could set up some simple 1D model and say, okay, this is what happens for stress dependence. This is what happens if it's the scale. And have you done some sort of line on that thing? Sort of to see just maybe conceptually, realizing that regionally 3D will matter and this and that and the other thing, but is there some general relationship you could put on that plot on the right? Just to put some numbers on what we just said.
I didn't quite follow. You mean about the 2D versus 3D thing? Or?
Well, no, you couldn't easily do that, but the moment magnitude tells us something about the dimension of the earthquake.
Yeah.
And so from that, you could say, given a typical, say, 1D viscosity model, for example, those are the sorts of reference times I would expect. And just to see if there's a simple relationship that could fit that.
Oh, I see. Okay. Yeah. You might be able to do it, but there. But the subduction zones are like they have different, even though they are governed by the same physics, but locally they all have a different depth, different convergence velocity, and a different shape of the margin. So it's kind of difficult. It's still every model is site specific. But the physics behind all these models is common. So we can see the trend, but the certainly with the complications, different parameters, difficult to provide. You can fit a line, but you can see like this here, this one, Geological, right? It obviously is a bit too slow. Why? Because the convergence rate is very, very low. right? So if you take into account, there's actually another figure in the published paper. If you take into account of that, that can come down. If it's not measured by time, measured by something else.
Right.
So there are all these other complications.
Yeah, I guess not to drag this on, but to see how far those points are away from a simple line would be to quantify how important those complications are.
Yes,
That's my
yeah.
Luke.
Kelin, very nice talk. Thanks very much. Yeah, I just curious, we this enhanced locking you're talking about, you just stated, but what would be, in your opinion, the physics that would cause that kind of behavior on a fault zone? I mean, it's really interesting, actually.
I'm not tremendously confident about this. You can imagine things happen. And also kind of similar things were reported by other people, like for southernmost California. And I think Roland Bergman's group, and they produced a paper. Kind of similar suddenly. It's easy to imagine how the fault lose stability, right? Suddenly it slipped, right? Yeah. But it's more difficult to imagine how it increases stability, right? And it's to me, if this is true, and that requires fault mechanics people to study it in the lab and in theory, right? But even though with the current mental the model with viscoelastic model, we cannot explain it without its enhanced locking. It cannot be ruled out. There might be something we haven't thought about. You may be able to explain it out in other ways instead of enhanced locking. I don't know, but so far this is the best explanation.
Yeah. I just was wondering, if you because that's talking about healing and all these properties is going to depend on the rheology of the specific rheology of the specific pore zone. So I thought, maybe you had some ideas, stuff like that. But yeah, in terms of Wright state, that's quite surprising that it has this kind of enhanced locking.
That's right. Yeah. And heal, like catastrophic healing is also quite. All of a sudden, all these minerals deposit, all of a sudden it steals something. Maybe appropriate pressure, or suddenly the fluid flows away, and
yeah. Okay.
So along those lines, how geographically local is that effect? If you had another map, like a bigger one.
Yeah. So basically about half of the
Is that where the ridge comes in?
The ridge is
down there.
Yeah. The rupture is terminated by the ridge in the south. So about half of the rupture zone, we've seen this, but we do not have measurements for the other half. We don't really know how far it goes northward.
So I mean, in terms of the thermal wedge structure, there might be a south-north gradient of some sort.
Yeah, there's some gradient. Yeah.
Thank you. Really enjoyed your talk. I was wondering, are there any potential interactions between the different kinds of subduction behavior you described and the background state that would be induced by glaciation and the uplift following the decay of ice sheets since the last glacial maximum?
It's a good question. Yeah, the question is the dominance of the process.
Yeah.
And it's quite interesting. I don't know if you've seen there was another paper and in geology we published, and it's just south of this. and there's that Chile ridge, and it's an important boundary. Observationally, to the north of it, the deformation is dominated by earthquake cycles. So we're still seeing the postseismic deformation of the 1960 earthquake, things moving that way horizontally mostly. But to the south is the Patagonian ice fields, right? And there we observe the fastest uplift on Earth today. And that's because of the ice melting. And we have modeled it And it still is it's fairly simple. If you have a Chile rig produces slab window, right? Slab window produces very low viscosity. And you have the ice melting up there, pretty small, even though pretty small, regionally pretty small, and locally it can produce very high uplift. So that's it. And so in that case, the whatever, if there's any earthquake cycle signal, well, the converges much slower. It's got to be very, very, very small. So everything is dominated by the ice melting. So it's different places, it depends. I guess for Alaska, maybe in some places they are equally important, right? And maybe Northern Cascadia, well, I guess Northern Cascadia is still mostly earthquake cycle signal. Yeah, I guess depends.
Yeah, thanks. Can I ask a quick follow-up? And just do you, because I come from an ice perspective, and earthquakes and the deeper part of the mantle is something I think about less, but I found your description of viscoelasticity and the connection to GIA very interesting. So during like 20,000 years ago, if you imagine either in Patagonian ice field or in Alaska, when you have an ice sheet that's several kilometers thick that extends to the coast, would the stress perturbations induced by the viscoelastic response to the ice sheet being there, like would those be on a similar order of magnitude to the kinds of stress that's building up because of the seismic displacement, or even with the ice sheet present, are the sort of orders of magnitude of that effect very different?
You're asking a very important question. And there was quite a bit of controversy in Northern Cascadia on a very question. And a while ago, like Roy Hyndman and I published some papers. At that time, we didn't have any horizontal, like those before GPS, no horizontal measurement, just leveling, right? And we saw these things, and we had to make corrections for GIA. We used ICE 5G and Peltry's model, right? And so that model gave us pretty big signal, and we made a correction. But later, my colleague Tom James, of course you know Tom James, right? And he used more local data and redid the GIA modeling, and it turned out in the new conclusions is the viscosity is so low for plate boundaries, right? And the global model, like Dick Peltry's global model, really would not apply if you use the local lower viscosity, and the GIA effect kind of it's already done. Yeah, so we don't really see it. We don't need that correction. So that was it's quite interesting. Yeah. So in later models, I was for some time I was quite frustrated with this. There are other things in the vertical direction I could not explain, still not explained. I was quite frustrated. So from a certain time, like yeah, I began to look at horizontal only because GPS came out with beautiful data. Now it's time to go back, look at vertical again, to re-examine these things. Yeah, but I think that Tom James' conclusion is fairly robust, and the conclusion that GIA effect for the previous ice age is quite small. It can be neglected. Is okay for Northern Cascadia. For other places, it depends on the viscosity.
Fascinating. Thank you so much.
Quick note, what is interesting also is that if you allow for non-Newtonian viscosity, where the stress matters, the superposition of GIA and sort of background mantle flow can make the viscosity anisotropic, which is a thing that was pointed out by Howard Schmeling like in the 80s. So there are some interesting things that even give you directional dependence when you superimpose those scales. And I think given the interest on the response of the deep earth, right, on the ice sheet stability, those might be worthwhile revisiting. So it's fun stuff. And Aaron looks not excited about that.
Yeah, I just need some help for the last part. You know, the energy part. You use this. You know, you present it really nicely. You use this very simple model. You know, you with an elastic dislocation, viscoelastic lower crust, a mantle, and yeah. And you show how, in some places how, you know, the arctangent is kind of behind what it's expected, basically, is what you're saying. And I kind of think about it as mean that there is more, you know, it's not fully elastic, it's more possibly more dissipative processes, you know, and elastic processes that would get rid of the energy, you know, before, you know, and basically slow down the accumulation of elastic strain and make the period longer, the recurrence time longer. Did I get it, or?
Is no, in this model, the recurrence interval is prescribed.
Okay.
We want to see the effect. What controls the recurrence interval?
Okay.
That can be many other geological fault parameters, right? But normally you would expect the with faster convergence slip rate, geological slip rate, recurrence interval might be smaller, which is indeed right? So there is some correlation. Yeah. So, but to explain this story is fixed. And so story is because it's because the reason is because the viscoelastic mantle takes its own life, right? You have an earthquake, then you have then you have repeatedly, then it just keeps flowing. It keeps flowing, and it keeps flowing. Then after the earthquake, when the fault is locked, this one is still flowing, so it lowers the fault very quickly. Then it itself will relax, will slow down. But the damage is already done. It's already energy already accumulated. Yeah, and it becomes slower and slower.
Right. But there is this interesting thing, right, that you get very early reloading through that. And there are papers involving Bonafede and others that suggest that the earthquake cycle actually becomes shorter because of the viscoelastic stuff. And so this is, I was discussing this with Eric Dunham, right? And so I think this is quite subtle and it depends on how you set it up. But there are ways where this works out, where it becomes actually faster viscously.
Yeah, well, just on that point, actually in this little paper, we had a discussion about how this may affect the kind of the randomness of the recurrence interval. You see the fault is loaded very quickly, right? And half of the cycle, the second half cycle, it stays on the verge of failure, actually. So any perturbation by other regions can cause earthquake to occur.
Exactly, right? Because you're so close to it.
That's right. Yeah. So that explains, I think that explains also is consistent with some of the geological observations. For long recurrence faults, the recurrence interval seems to be very irregular. For short recurrence faults and faster convergence slip rate, and the recurrence seems to be more regular. So that's consistent. Yeah.
And while we have this up, so this whole business, right, with this arc10, it's well known, right, that there's a trade-off between what you interpret as locking depth inelastically in the viscoelastic cycle, and people have used that, for example, to argue that long-term and short-term strain accumulation are consistent for California, right? And so we know that there's this trade-off between the viscoelastic stuff and what Liz Hearn called ghost transients and things like that, and the elastic interpretation. So I wonder on that point, so what are you adding here with that analysis?
Well, apparently, if the recurrence interval is short enough compared to a relaxation time, and the elastic model works fine, right? So that's one thing. And if it's not, elastic model doesn't really work. One important message is a lot of people were like, you see the literature is saturated by the claim that earthquake potential is related with what we observe today. If you see high strain rate, there's a lot of strain accumulation in earthquakes. So that's not quite, that's conflating strain rate with displacement, right? With strain, yeah, velocity with displacement. So that's just a reminder. And this in the early days, when Jim Savage and other people, like in early days when they published this kind of viscous models, they were not talking about velocity. They were always talking about just the displacements. But however, since geodetic observations became available, that's all we can only observe velocity. We cannot observe actual displacement, right? And then people forget this and just keep talking about velocities. So that's why now this serves as a reminder. Let's think about velocities.
Thanks. Going back to GIA for a moment, just an observation that another place where there's very high uplift rates from GIA are the Amazon embayment along the coast of West Antarctica, where that's modeled to be related to very low viscosity in the asthenosphere. But subduction there stopped 100 million years ago. How long might you expect the effect of the heat, excess heat in the mantle wedge to last? Subduction went on from 300 to 100 million years ago, but then quit.
That's all gone. Yeah.
And uplift rates are about up to 50 millimeters a year there.
Yeah, thermal relaxation. Suppose you have subduction. Suppose subduction stopped all of a sudden today, and it'll take of course depending on how cold, how warm. If for cascade young slab, right, it may take on the order of 30-40 million years for the whole thing to become like no subduction neck. If for old slab like Northeast Japan, it may take longer. How long? Yeah, maybe up to 100 million years. Yeah, maybe, but still very, very slow, very, very slowly. It's the mantle wedge is cold, right? And it'll warm up. And the slab, suppose slab suddenly stop, right? And it'll warm up. But if the cessation of subduction is for other reason, and the slab breaks off or whatever, it'll be much faster. You suddenly prevent a lot of heat from below. The slowest case would be the slab stalled. It suddenly stops there. It takes a long time to warm it up. Even that, I think, for old slab, maybe on the order of 100 million years. But that's usually slab subduction cessation is probably more dramatic than just slab stopping.
This was probably ridge crest subduction that stopped it, the relative
Yeah,
motion.
then it's hot. Yeah, then it wouldn't take very long.
Thank you.
All right, we're at the end of our session. Unless there is another final burning question, let's thank Dr. Wang again for a great presentation.
Thank you. Thank you.